So the last part of ANOVA that we're going to have a look at is the Latin square design. So this is where we have two blocking factors. And unfortunately we do have to do this whole thing by hand, so do make sure that you check it very carefully. Again, we can have a look at inherent random variation. We can have a look at the difference between means to try and tell if we've got any difference there. And we have similar three assumptions, which is that there's no interaction between the three factors. We've got a common variance, and that the each factor level combination is approximately normally distributed. And again, we have some formulas here which we are actually going to be using this time. And as you can see, before we had between the rows and between the columns, now we have between the rows, between the columns and between the letters with our residual and our total. And we're going to have a look at how we are going to be doing this. So this example that we're going to do first is quite a long and tricky one. The reason why it's quite long and tricky is because usually we would be given this data in a table that looks like this one here, okay, where we've got one variable across the top, one variable down the side, and the other one in the boxes. But for this question here, we've been given it in three lists, and then our variable there, dependent. And I'm going to show you how to get from a list like this into a table like the one I just showed you. So across the top, I am going to put fuel. Down the side, I'm going to put speed. And then in the boxes, I'm going to put time, the car, sorry. So fuel is A, B, C. Speed is 50, 75, 100. So then for the first car, we've got 50 and B. So 50 and B, that was 347.8, and that was car 1. Then here we've got 75 and C, which is 331.4, and that was also car type 1. Then we've got 100 and A, which is 275.8, and that is also car 1. Then we've got car type 2, 50 and A, which is 365.4. Then we've got 75 and B, which gives us 339.8. And then we've got 100 and C, which gives us 298.9, and that was also for car type 2. And then we've got 50 and C, so 50 and C got 318.9, and that was car type 3. Then we've got 75 and A, that was 302.2, and that was car type 3. And then we've got 100 and B, which is 271.8 and 3. So this is how we go from lists like this to our table, and we can see that with the car types, we've got each one only appears once in each row, and each one also only appears once in each column. So in this case here, we're looking at between the brands of petrol, so we're looking at between the fuel. So our H0 is going to be that mu I equals mu for all I equals, and I'm going to go for ABC this time because that's the letters that we have there. H1 mu I is not equal to mu for some I equals ABC, where at least two differ. And mu I is the population mean, and this is distance, yes, travelled on fuel type I. So then I'm going to try and find the totals that I'll need. So I'm going to have to find the total for each row. I'm going to have total, total, total. Then we're going to have, oops, sorry, these are just R1, R2, R3. Don't need the T's on them. So we've got R1, R2, and R3, which are going to be the totals for our rows. We're going to have C1, C2, and C3, which are going to be the totals for our columns. And we're going to have L1, L2, and L3, which is going to be the totals for our car types. So for the first one, for the rows, we're going to have 365.4 plus 347.8 plus 318.9, which gives me 1032.1. Then for row 2, we've got 302.2, 339.8, and then 331.4, which gives me 973.4. And then lastly, we've got 275.8 plus 271.8 plus 298.9, which gives us 846.5. So now I'm going to do the same for the columns. So we've got 365.4 plus 302.2 plus 275.8, which gives us 943.4. Then we're going to have 347.8 plus 339.8 plus 271.8, which gives us 959.4. And then lastly for the columns, 318.9 plus 331.4 plus 298.9, which gives us 949.2. Then for the letters, it's probably easier to do it up here because we've got the car types all together, but you can pick it out from the table here, adding the blue ones together, the green ones together, and the purple ones together with the way that I've written it there. So we're going to have 347.8 plus 331.4 plus 275.8, which gives us 955. Then we're going to have 365.4 plus 339.8 plus 298.9, which gives us 1004.1. And then lastly, we're going to have 318.9 plus 302.2 plus 271.8, which gives us 892.8. Sorry, 0.9. Now, just as we did when we had a look at the long version for the one Factor Anova, we also need to find the overall total. And this is also good to make sure that we've added the other things up correctly. Because if I add my rows together, that should give me the same number as if I added my columns together, which should give me the same number as if I added my letters together. So my rows, I've got 1032.1 plus 973.4 plus 846.5, which gives me 2,852. So I can check this with my columns. So we've got 943.4 plus 959.4 plus 949.2 and I've seen that I've typed this in wrong. So it's 943.4. Yes, which gives me the same number. And then hopefully when I type my letters in, so 955, 1004.1 and 892.9, and that also gives me the same total. So like we said before when we're having a look at the two-factor ANOVA, because each one of, well, the example that we had there was the compilers had to run each of the program. Here the cars have to all have the same fuels, have to all go the same speeds. So we're going to have a 333 here, but we could have a 444 or a 555. Okay, it will always be that we have the same number of each one of our factors. So my N is going to be the number, Ni is going to be the number of each factor that I have, which is 3. And my overall N is 9 because I've got 3 lots of 3 here, this my little table here. The last thing that I need to figure out is the sum of the xi, j, k squareds. So that means that I need to square each of these numbers and add them together. So I'm going to have 365.4 squared plus 347.8 squared plus 318.9 squared plus 302.2 squared plus 339.8 squared plus 331.4 squared plus 275.8 squared plus 271.8 squared plus 298.9 squared, and then just quickly putting that into my calculator. So I've just typed that into my calculator here, and that's given me 912,076.14. So now I want to start to use those formulas that I was talking about before. So the first thing I'm going to find is my SST, which is going to be the sum of the xijk squared. So that's going to be 912,076.14 minus t squared, which is 2,852 over n. So that gives me 8,309.028889. So the second thing I'm going to try and find is my SSRs. So my SSR is going to be each one of these totals for my rows squared divided by the number of pieces of data I have in my row, which is 3. So then 973.4 squared over 3 plus 846.5 squared over 3 minus again my t squared over n. So that gives me 5,999.6288889. Then we're going to do the same for the columns. So our SSCs is 943.4 squared over 3 plus 959.4 squared over 3 plus 949.2 squared over 3 minus 2,852 squared over 9. So I'm putting that into our calculator. So that gives us 43.74222222. And then lastly we need to have SSL, well, second to last. So that means that we're going to have our different totals for our L's. So that's 955 squared over 3 plus 1004.1 squared over 3 plus 892.9 squared over 3 minus 2852 squared over 9. And that gives me 2070.295556. So the last one that I need to calculate before I can make my table is my SSE, which is going to be my SST minus my other SS's, so minus 5,999.628889 minus 43.74222222 minus 2070.295556, which gives 195.3622218. So now we can start to make our table. So we're going to have between the rows, which was speed, then between the columns, which was fuel, then L's, which is car, then we've got our residual or error, and then we have our total. And across the top we're going to have SS, DF, MS, SF. So the SS's, we've already calculated all those. So we're going to have 8,309.029. I'll just round these to three decimal places. Then SSR, we've got 5,999.629. Then we've got 43.742, 2070.296, and then for the residual, we've got 195.362. So then for the degrees of freedom, well, we've got 3 different speeds. So 3 minus 1 is 2. We've got 3 different fuels. 3 minus 1 is 2. We've got 3 different cars. 3 minus 1 is 2. We've got 9 pieces of data in total. 9 minus 1 is 8, which means that our missing number here is going to be 2. Then for the mean of the sum of the squares, remember that we're going to divide the sum of the squares by the degrees of freedom. So we're going to have 5,999.629 divided by 2. Which gives me 2,999.815, then 43.742 divided by 2, which gives me 21.871, then 2070.296 divided by 2, which gives me 1035.148, then 195.362 divided by 2, which gives me 97.681. So to find the test statistics, and this time we are going to have 3 because we're controlling 2 and we're testing 1. We're going to do the mean of the sum of the squares of that group divided by the mean of the sum of the squares of the residual. So we're going to have 2,999.815 divided by 97.681, which gives us 30.7. Then we're going to have 21.871 divided by 97.681, which gives us 0.224. And lastly, we're going to have 1035.148 divided by 97.681, which gives us 10.6. So here we were testing with our fuels, which means that our test statistic is going to be 0.224. To read off our critical value, we're going to go across by the degrees of freedom of the fuel and down by the residual. And this was at a, doesn't tell us, so we're going to use a 5% significance level, which means that we're on page 22. So page 22, looking at the 0.95 table, going down by 2 and across by 2, which gives us a critical value of 19. So then as the test statistic is smaller than the critical value, we're going to accept H0 at a 5% significance level. There is insufficient evidence to suggest the mean distance travelled using the 3 fuels was not the same where at least 2 means differed. So as I said before, these are, if we have 3 of one thing, then we have to test that against 3 of each of the other 2 factors, which does mean that it's unlikely that you'd get one of these that's bigger than 4 by 4 because it can get quite tricky. You're more likely to only be asked to do a section of this because it does take so long to do. You might just be asked to, you know, if I have 2 blocking factors, what type of analysis would I run? So that'd be a Latin square design. So there's quite a lot that they can ask you about this without just flat asking for you to do a Latin square hypothesis test. Like I said, just because they do take quite a while to do. So thank you very much for listening, and please, if you've got the notes, try the Now You Try.